Hello everyone. Thanks for coming in at this early point in the morning if you're from the West Coast. So today we have Jared Kaplan, who's a physicist at Johns Hopkins University, talking to us actually about neural networks and this physics of neural networks in terms of scaling laws and the physics behind language models such as GPT-3. So Jerry is a theoretical physicist with broad interest in many things in physics like effective field theory, particle physics, cosmology, conformal field theory, and so on and so forth. But of course, today we're here to hear him talk about the physics that led to GPT-3. GPT-3 is a kind of maybe a divisive subject. There are probably two camps of people about this. The first camp would be like, hell yeah, like singularity has arrived. And then the second camp would probably be like, it's kind of disappointing that like intelligence at the end is just scaling up. But as Jared will show, that scaling up is never so simple, and there are actually like beautiful physics that can go on behind the scenes in terms of scaling up. So let's even if you're in the second camp, let's be a bit patient here today, and let's hear Jared explain the beautiful results behind GPT-3. So take it away, Jared.
Great, thank you. Okay, well, yeah, thanks a lot for the invitation. I'm very happy to be here and discuss this. Given that introduction, I should say I'll try to sell you on the idea that scaling laws are really one of the most fundamental things that's kind of going on with machine learning. And I think, at least if you're a physicist, this should not be discouraging. But anyway, you'll have to judge for yourself and ask lots of questions. So this is a brief outline for the talk. Since a lot of the talk is going to be about language models, although not all of the talk, I'll say some other some more general things, some more general claims. I'm going to sort of review what language modeling is in case you haven't thought about it very much, and what its motivations are, and I'll also briefly mention what a transformer is, because those will be the models that I'm using basically for everything in this talk. Then I'll talk about the scaling laws for language modeling. I worked with Sam McCandlish from about a year ago. I'll talk about some soon to be released results in brief about how universal these scaling laws are. And there's been a lot of other work on this kind of subject in the last few years, but I'll be talking about how it's universal in a lot of areas of generative modeling, and maybe some things that you would say go beyond generative modeling. I'll talk about how sort of the GPT-3 model, what it is, kind of how it was significantly motivated by this way of thinking about how machine learning works. And I'll talk about in-context learning or meta learning for GPT-3. And maybe if there's time, I'll have like a slide or two about some work I've done with a student, Yudkar Sharma, and some ongoing work with other people like Jae-Hoon Lee, Ethan Dyer, Yasemin Bari, and Yudkarsh on trying to come up with something like a theory that explains these scaling laws, because I think one of the most striking things about them is that they're very, very precise. They're not a kind of a squiggly, they're not a squiggly sign as much as physicists we love squiggly signs and order of magnitude estimates. So first, let me talk about why language modeling and what language modeling is, and briefly what a transformer is. So I think one reason why, if you care about making progress in AI, it's very interesting to study and model language, is that language is our species' best attempt to encode everything about the world. We want language to be able to describe anything that can happen as efficiently as possible. And so there's a sense in which there's a lot less noise, a lot less waste in language than in other data modalities, and that might give you hope that you can learn a lot from it in a relatively data efficient way. Of course, there's also a huge quantity of writing freely available on the internet, and I don't have access to the Library of Congress. I mean, OpenAI doesn't. There's no secret pact there, but there's something like 10 million books in the Library of Congress. You might guess that that's something like 1 trillion words. So there's really a lot of really high quality language out there that could be learned from in the future. And of course, the internet is much bigger than this. And another motivation is that an AI that really understands or can communicate in natural language can be, you can ask it about anything. You can get a lot of intuition from its responses. You can try to train it to, if it understands language, if it knows what words mean in some sense, then you can try to train it using that information. And that also might help us to sort of understand what machine learning systems are doing and sort of how we can make them safe, make them aligned with like what we want them to do with our values, et cetera. So those are some motivations for studying language. So the language models I'll be talking about are just autoregressive. So all they're doing is learning language by predicting the next word in sequences of words. So we have this conditional probability distribution for word n+1 given the first n words. And we're just trying to maximize the log likelihood of real text, which is for us sort of the right answer for this probability distribution. And really that's all there is to the objective. And if you're giving a colloquium or a journal club, you might expect that elephant. And when I said the word elephant, that was kind of weird. It wasn't the word that you were trying to expect, that you were expecting as a human, I imagine. And similarly, that's true for these trained models. So if I say as a speaker at a journal club, you're probably elephant me to say certain things, the model thinks that what I'm going to say in place of elephant is not, or going to, or going, or used, or expected. All those things seem reasonable in that context. And it assigns an explicit probability, though, to elephant, which is something like 10 to the minus 8. So it's very rare for that to happen. And this is sort of the probability distribution of next word prediction in action. And so how do you train these models? Well, you turn words, or more generally tokens, which might be words, or they might be subwords or letters, or whatever it is that you use to parse language. You turn words into vectors via some embedding space, and that embedding space is itself learned, and it encodes interesting structure that it learns about language. So for example, maybe king minus queen and man minus woman are sort of the same vector in this high dimensional embedding space. There are a lot of interesting relations there. One of the most commonly used models for modeling language up until a few years ago was the LSTM, which is a kind of a fancier recurrent neural network, which works by taking in some prior context word by word. It does some processing on that context, the embedded token, and then it passes that information. It remembers something. It passes that information along to the next version of itself while producing some output. And so that's one very, very natural way that you can imagine reading sentences and trying to learn the probability distribution of words or tokens, is by looking one token at a time and saving some information, moving on, et cetera, and making a prediction at each token. So that's that I'm including just because I'll have one plot that mentions LSTMs. So for context, the kind of model, however, that I'll be studying for almost everything else in this talk is the transformer language models and transformer models in general. And if you're an expert, everything I'll be doing will be with purely decoder-only transformers. So if you know what that means, then fine. If not, it won't really matter for the talk. But transformers have been a big deal, and they're based on attention or self-attention. And this little diagram is trying to illustrate the idea that really all attention is a highlighter. The model literally looks at all of the words in the sentence at once, and at each layer it highlights, which means mathematically it takes some weighted linear combination of the previous entries, which for the first layer are literally the tokens or words. It takes that linear combination, then it thinks about them, it performs some simple processing on that linear combination, and then it it takes it out, the outputs of that layer and does the same thing again and again and again until finally at the end it makes a prediction for all of the next tokens or next words at every position. And so that is what a transformer does intuitively. And since this is since I'm not sure, this might be a somewhat technical audience, there are a lot of people have studied machine learning. This also shows mathematically what's going on. So you can think about the data after you take many, many sentences or paragraphs and you convert them into tokens and then embed them. You have many different vectors. And so those vectors have some sequence position index S, and they have some embedding index E, which is sort of the index of the vector space for each embedded token. And then what self-attention is it's this formula. So what's going on is we take each token, each embedded vector, and we map it to some smaller subspace with keys and queries, which are some via some learned parameters W. And then we look at the overlaps of these keys and queries. So the idea is that if in one particular position, given what the model has processed so far, if a particular other kind of word is going to be useful information, then these key query overlaps can be big. If it's not going to be useful information, then they can be small. And then we perform this softmax, and basically that's what's doing this highlighting of bringing to our attention the other words, tokens in the sequence that are relevant, and ignoring the ones that aren't, for whatever the model is learning to do. So that's how the self-attention mechanism works very quickly. Transformers combine this with some fully connected processing and some residual connections. And that's all that there really is to the models that I'll be talking about today. So you can do a lot of things with these models. So these are two relatively recent samples. On the left, we have a sample of a poem written by GPT-3, just based on the title Shadows on the Way by Wallace Stevens. And if you're into poetry, I mean, I like poetry quite a bit, then you might notice, if you've read a lot of Wallace Stevens, this is a pretty good reproduction of Wallace Stevens' style. It's a pretty impressive poem, I think, given that it was just written by an AI all by itself. And on the right, we have images that are being described pixel by pixel. So you can ignore the 2D structure and to some degree in the image and just look at it as a sequence of pixels and try to generate an image by sampling from the autoregressive probability distribution pixel by pixel. And this is some work by Mark Chen and others at OpenAI. And you can see that you can get really impressive photorealistic images of a large, diverse set of different kinds just via this model. So it's exactly the same model. We're just, in one case, calling tokens words. In the other case, we're calling tokens pixels. And in both cases, the model learns, I think, a very impressive amount of structure in the data. So now I want to talk about scaling laws for neural models. And really, since this is a talk for physicists interested in ML, I'm going to start at a very, 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 very big picture level. Then I'll talk about scaling laws. And then really, most of what I'll show you is empirical results. I think in machine learning, there's a huge amount of room for a lot of experimentation and empirical exploration. So that's mostly what I'll be showing you. So I guess there are two motivations, two ways of saying maybe the same motivation. So one is sort of, why does machine learning work so well? At least if you believe that it's working well. I think it's working very impressively. What matters and what doesn't? So what about machine learning? Is it the algorithms, the architectures, the choice of loss function, the data set? What is it that sort of matters and what doesn't? And I think this matters a lot to me because I always want to work on the thing that seems like it's going to be most important and maybe easiest to make progress on. And so I think this tells us something about what kind of research problems we should work on, how we should think about the future of the field. And I think another way of framing this that I at least had in mind, say 4 or 5 years ago, before I started really even learning in detail about all the recent progress that's been made over the last 10 years, is making progress on artificial intelligence something kind of like trying to prove the Riemann hypothesis, or is it more like, say, building a really powerful steam engine? And I think, for me at least, intuitively, proving the Riemann hypothesis is something where only an expert who spends maybe a lifetime studying the problem is going to make progress. They have to be some kind of genius, whatever that means. Probably there will be some sense in which at least there's kind of like flashes of insight involved or turning points in the research that are very, very hard to anticipate. And so that means that progress is going to be very hard to predict and hard to foresee, especially if you're not one of the few experts in the field, et cetera. So that's one framing of what AI might be like. And another is that it's like building steam engines where there's both a lot of science and a lot of engineering involved in building better steam engines. But in terms of the science, a lot of the science is kind of thermodynamics, understanding certain kinds of scaling relations and scaling laws, understanding kind of what fundamental limits exist in terms of efficiency, in terms of energy, things like that. And then it's really a question of kind of following what's suggested by these scaling laws while avoiding bottlenecks, avoiding kind of pitfalls, and there's kind of a clear trajectory of chartable progress. And probably very obviously, I'm going to be suggesting to you that it seems like it's possible to make progress in just AI capabilities by working more the same way that you'd work to build a better steam engine rather than proving the Riemann hypothesis. So in kind of summary, what I'll be trying to argue and showing you empirical results for is that there are quite precise scaling laws for the performance of machine learning models as a function of ingredients such as the number of model parameters, the data set size, the total compute budget used for training. And I should also say that I think these scaling laws are kind of everywhere in machine learning. They're not just about these ingredients. I'll be talking primarily about these ingredients, but I think taking this perspective that maybe if you make a log plot, you'll see a really nice trend, and maybe that trend means something and can suggest what's going on. I think that general perspective is extremely useful and kind of universally useful. Basically, everything I've worked on, there are these kind of scaling laws lurking around everywhere, and I think they're very useful for thinking about what's happening. And then probably more controversially, in at least some cases, I'll kind of be suggesting that a lot of the other details might not matter as much as some of these as these scaling laws and the basic ingredients and sort of what they suggest. And maybe very surprisingly, at least in some cases that we've tested, it seems like improvements in what you might call the machine learning algorithm mostly just change some sort of overall constant prefactor. Now, if you're an engineer or you're building a startup or something, maybe you care a huge amount about whether or not your model is going to be 3 times more efficient than another model. I think that obviously matters. But if you're coming from theoretical physics and you're used to doing things like conformal field theory and string theory, you're sort of used to thinking like, well, the thing that matters most is something like the scaling. And of course, the prefactor definitely does matter in detail. But in terms of making kind of very big picture forecasts and understanding what goes on, it might not be so crucial. So I don't want to say that nothing else besides scaling matters. That's certainly wrong. But understanding how it matters, for example, that it usually is just kind of a prefactor, I think is kind of interesting. And another point that I want to make, because it's sort of a more first order rather than 0th order point. So at 0th order, a lot of people might see the first bullet point and say, oh, wow, okay, so all we have to do is scale things up. And I think there's some sense in which at 0th order, something like that might be true. But I think there are a lot of other lessons about this, which is that a lot of improvements in performance are about avoiding bottlenecks in machine learning systems. So some obvious bottlenecks are things like you have a really big model, but you don't have enough data. You have a lot of data, but you're training a very small model. You just don't have enough compute. You're not training long enough, something like that. But then, of course, there are other kinds of more literal, say, bad information propagation bottlenecks. And I mean, I think about this via this cartoon equation, which is just that if you act with a matrix 1,000 times on some vector, then basically you're just going to be dominated by the eigenspace of the largest eigenvalues, and so you can lose information. And I think, at least, I mean, I'd be interested in if people disagree, but I think a lot of the most highly cited papers in all of machine learning are really all solving a bad information propagation problem. I think there's a sense in which transformers are doing that. There's a sense in which ResNets are doing that. There's a sense in which batch norm and layer norm and ideas of that sort are all doing that. So I think identifying bad information propagation and solving it is a big deal. It can get you 50,000 citations. And I think that's where a lot of the big results have been in machine learning. And I think we can kind of categorize them together in this way. Okay, so now I want to just talk about what the scaling laws are. And this will mostly be an empirical discussion, except maybe at the very end of the talk. These plots aren't too complicated, but let's start at the far right. So on the far right, what we did was we had a really, really big language data set. So we were not limited by how much data we had. And we trained a large number of different GPT type transformer models on the autoregressive next word prediction task. And these models had various different sizes. And you note that it says non-embedding underneath parameters. So we're not counting the dimension of the parameter space. It turns out just counting the number of parameters and just sort of the transformer torso is where you get a very, very nice scaling relation. But if you do this and you make a log plot, then you see over something like 4 or 5 orders of magnitude in model size, there's an extremely precise scaling law for the loss, which is just the log prob averaged over all of the tokens, as a function, the test loss as a function of model size. The middle plot is the same thing, where we take a really big model and we train it with various different size data sets, and we just use early stopping. So we just stop, we just record the test loss at its minimum during training. And you also get a very, very nice scaling law with respect to data set size. I mean, these kinds of scaling laws have been observed in other prior works as well. And then finally, on the left, this plot is a little bit more complicated. So we have these light blue curves. All of those light blue curves are learning curves. And the reason why the learning curves are shifted left and right is because the total amount of compute you use during training is, roughly speaking, proportional to the number of parameters in the model times the number of tokens that you process during all of training. And so models with more parameters have correspondingly use more compute per training step. And that means on a log plot, they just get shifted left or right by a constant. And so what you see is we have all of these different learning curves, and then we can ask what is the sort of frontier of performance. That's what this black line and the fit to it, this orange line, are. And we're asking sort of what's the best performance you can get as a function of compute, given that you've trained all these different models. And different models win, they do best at different model sizes at different amounts of compute. But you see, you get this another very, very nice sort of power law frontier for the best test loss you can achieve as a function of the computational budget. And I want to emphasize that in all these cases, we're sort of not letting anything bottleneck performance other than what we're studying. So with compute, we have many different model sizes, but we have plenty of data. With data set size, we have a very big model. With model size, we have plenty of data. And the compute budgets here are written in petaflop days, which is about 9 times 10 to the 19 floating point operations. That's what a petaflop day is. And I mean, I personally just find it mind-boggling that that we've been able to build computers that are so powerful that we can sort of do that many computations realistically. I mean, GPT-3 is trained with something starting to approach like Avogadro's number of floating point operations, and it's just kind of crazy. So the other thing that you can do with
there's a question. I don't know if you can see the chat. Just briefly, because it seems like an easy question, you can just answer here.
Sure.
So the y-axis says test loss, but you mentioned you take the minimum loss during training.
Yeah. So for For the parameter and compute plots, this is just the test loss. Well, so for the compute plot, it's just test loss because all of these are learning curves. You see what the learning curves actually look like. For the parameter scan, we're using the test loss at the end of training, which is always the lowest. For the dataset size scan, that's the only place where it's subtle. We're using the early stopped test loss.
So actually, my question, if you don't early stop, like how much difference does it make?
Well, I mean, if you train forever, then I think the loss could just go up a huge amount, and you could like dramatically overfit. So I think it makes a big difference.
But does it? Like usually you don't see that, right? Like it kind of converges at some point.
I mean, I think it's a good question. I haven't made the plot without early stopping, so I'm not sure. I'm not sure what happens in that case. I think it would depend on how long you trained.
Sure. And also to everyone, I think you'll be fine if you just shout out any questions you have. I mean, you can also type it in the chat if you're a bit shy, but you know, I think we're like light enough that we can handle prompt to questions. So thanks. I'll keep going.
Cool. So so this slide really makes reference to the compute plot in the previous slide. So on the compute, maybe I'll just go back to make that clear. On this compute versus test loss plot, we have all the different learning curves for many, many models of all sorts of different sizes. And you can ask sort of, when is it that a model of a given size is tangent to this orange line or the black line? When is it that a particular model size is at the frontier? Because whenever a model of particular size is at the frontier, it means that if you had a total compute budget of that much compute, you'd do best, you'd get the best performance by training a model of that size. And so then you can make a plot of what is the optimal model size to use for a given amount of computation that you're willing to do during training. And that's what this in a somewhat more cartoon form is indicating. What happens as you scale up the amount of computation? How do you want to spend it if you're going to try to get the optimal performance? And what's interesting here is you want to spend most of that extra compute on training a larger model. So, I mean, if you have something like 9 orders of magnitude in compute that you're adding, you might want to spend 6 of those orders of magnitude on model size and only 3 orders of magnitude on more processing, more training data. And at least I thought this was sort of surprising. When we first noticed this, you might have thought that you want to spend more of your compute budget on data, but actually you really benefit a lot by training larger models. So there are a few examples here about how architecture is and isn't less important. So on the plot on the left, we have a comparison of LSTMs to transformers on exactly the same data and the same task for parameter count. And on the one hand, you see that the transformer is doing a lot better than the LSTM. But I actually find it very striking that the LSTM for a very large range of model size is scaling in almost identically the same way in terms of the scaling exponent. So even this enormous advance from LSTMs to transformers looks like it mostly changed a prefactor in the scaling law rather than the scaling law itself. Now, an exception to that is suggested by the plot on the right, which is that LSTMs perhaps create a bottleneck. LSTMs, despite their name of sort of long short-term memory units, they're not great at remembering information over very, very long time scales or distance scales in the language itself, like distances among different tokens. And so while the transformers continues to improve with the position in the context, namely when the transformer reads more text, it's getting better and better and better at making predictions, the LSTM tends to plateau around sort of 100 tokens or so. And so this is one way in which the transformer is really doing kind of qualitatively better than the LSTM. But other than that issue with the bottleneck, I mean, the scaling laws are actually surprisingly kind of similar. And there are a lot of other examples you can find just playing around with the transformer architecture itself and its hyperparameters. So you can change a bunch of different hyperparameters like the depth of the model versus the width of the model, the dimension of the attention heads, or the ratio of sort of how much feed forward computation you do in a given layer versus how much attention computation you do. And in wide ranges, this doesn't matter that much. You can maybe change these hyperparameters by a factor of 3 in either direction, and performance only changes by maybe less than 1% in terms of the loss that different models of various sizes achieve. And so a lot of these hyperparameters, I mean, you can tune them, but they don't actually make a huge difference in terms of performance.
So just a common, I think so on the previous slide, like the y-axis for the bottom plots goes up to 10%.
Mm-hmm.
Any researcher who gets a gain of 10% or regress by 10%, that's like a pretty big deal for a paper. So like in that sense, I think maybe it's a overclaim that these things don't matter, but I get your point that like this is like a prefactor, which maybe like in the large scale, like grand scheme of things, doesn't matter as much.
I mean, I would push back against that. I mean, the y-axis goes up to 10%, but I mean, for the attention head dimension, I mean, all of the change is less than 1%, except, I mean, if you change it by a factor of, I don't know, 15 or 20 or something. And I think, I mean, also for the aspect ratio, I mean, these numbers are all, I mean, 10% is the limit, but I mean, most of the change is sort of less than 2%. If you change by about within an order of magnitude range, I think that's true for all of these. So, so I don't know. I would say that I just don't think it. I mean, I think it matters. It's worth optimizing, but and not only is it worth optimizing, but there's some best value, and the best value seems like it's actually independent of scale. So if you optimize this with a small model, you can then apply it to a larger model and probably maintain optimality. But I think it just sort of isn't actually that big of a deal.
Yeah, but like, so suppose like, suppose the literature is actually at the suboptimal point and people don't know or don't have enough compute to figure out to try to search for it. Or maybe perhaps in your experiments, there's some hyperparameter that isn't optimal, but you didn't tune because you didn't think of it. Then in which case you could make a difference. Again, like I think it's probably a prefactor, give you 10% boost in performance perhaps. But in the grand scheme of things, maybe it's not so important. But I guess like in the if you think about like an average researcher in LMP, if they can get like a 10% gain on super glue, then that's like a pretty big deal.
Well, this isn't a 10% gain on super glue. It just
I know. Yeah. I'm just saying like, if 10% on something like on loss, I think like from my experience, 10% like on BERT loss, an increase of 10% or decrease of 10% on BERT loss is like actually pretty significant. Like,
yeah, I mean, I guess the quantitative comparison we can make, I mean, first of all, like I said, I think it's not 10%, I think it's 2%, but if we look at doubling model size, like you can see there's this nice scaling law for transformers. If we talk about doubling model size, it seems like that's something like, let's see, I'm just sort of staring at the plot myself. I don't know, it seems like that's probably like 5 or 10% improvement every time. And that's something that you can just keep doing that if you can afford to do that. So it's something where there's a thing that you can sort of uniformly keep scaling up, and you're just going to keep doing better. Whereas these that have local minima, they're quite broad, and it's just a few percent if you're off by a factor of a few.
Yeah, I agree. I'm just saying, like, if you're submitting in Europe or something, and you're comparing, your method, and if your method, say like you can control for a parameter count and get 10% gain, that's a pretty impressive thing. And kind of on the converse side, if nowadays NeurIPS will reject paper that would just like double the number of parameters and get a better number.
Okay. Well, I don't really know. I mean, I'm not trying to optimize for NeurIPS, so
I know. I'm just saying, like, from a different perspective, these gains or these differences in performance is actually significant. And I do agree that conferences have weird incentives, but this is just an example of in terms of like micro progresses that we're making in terms of NLP.
Cool. Well, yeah,
But yeah,
I don't think we should probably spend more time on it. But yeah, I mean, the plots are the plots.
Jared, can I ask another question?
Yeah, sure.
Related?
Yeah.
Looking at these plots, you're using parameters and sort of saying there's a nice scaling law with respect to parameters. And I don't know if you, I missed if you mentioned this, but naively, for the same number of parameters, I can have an extremely linear network or an extremely deep network.
Oh, great. Yeah.
How much does that figure into it? Because I would imagine, you might be looking, well, it seems it works but maybe you're fixing the depth and then tweaking the parameters.
Oh, great. So, yeah, great question. Yeah. So for all of these, I'm fixing the aspect ratio. So in this middle plot, you see that the best performance is basically for an aspect ratio for a language model of about 100 between sort of this basically width model, width parameter D model and the number of layers. And so we're scaling up parameter count while keeping the aspect ratio fixed.
Sorry, if I read that plot correctly, you're also saying the aspect ratio doesn't have a huge impact within like over two decades or so. Is that what that plot is saying, the middle plot?
That plot is both saying that the aspect ratio doesn't have a lot of effect within 2 decades, but also what we did in order to make the plot on the sort of top left for transformers is to keep the aspect ratio roughly constant and scale up. I think it was roughly constant, but it wasn't exactly precisely constant, but yeah.
All right. And this is also basically transformers LSTMs. I mean, I'm just trying to imagine a situation where, for instance, parameters and compute are not linearly related to each other, because you're kind of claiming everything is sort of has a nice logarithmic relationship. And I guess in these contexts, parameters and compute and everything are linearly related, but you can imagine architectures where that's not the case. And I would want to know which one of these breaks in that sense,
Absolutely, yeah.
And depth is one parameter you can tune to get that effect.
Yeah, I know. I think that's a good question. So I mean, maybe EfficientNet is a natural like reference point for that. I mean, they're not studying a transformer. They have some similar scaling law, though I think they, instead of having, say, like the aspect ratio fixed, I think they have like a power of D model over a power of N layers fixed. But it's kind of a similar idea. But yeah, I agree. I think like for convs, like parameter count and compute are not linearly related.
All right, thanks.
Cool. But yeah, I would advocate, if you are like practically going to train a transformer, I think like figuring out what aspect ratio of width versus depth is best, and then scaling up, preserving that is I think the best thing to do. And the ideal aspect ratio is different for different data sets. Okay, so this was just, let's see, I mean, maybe I should be going a little bit faster. This is just some more information about loss versus position and context, because I think it's important to note that many things are not universal, and some things I think are and some things aren't. So on the top left, we have sort of loss versus token index, which is just sort of how many words you've seen up until that point. And these actually have some nice power law form. I think, I mean, I guess this is a hypothesis, that this is really about power law correlations in language, that the top plot in the top left has a power law form. But if you look at loss versus position and context for, say, a pixel by pixel transformer image model, the loss as a function of where you are in the context is not a power law at all. It looks like these images at the bottom, where the loss is bigger in the middle of the image and smaller near the edges. I think this makes sense because a lot of the complexity in images is typically near the center, but I just want to emphasize that there are scaling laws that are not universal across data sets, but I'm now going to talk about some features that do seem to be surprisingly universal. Also, there are many other useful things that you can study. So there are quite nice multivariable scaling relations. So this is an example for language models as we vary both model size and data set size. And you can use these to make predictions like, how much data do I need to keep overfitting under some amount? And again, this is with early stopping. I guess we've done these experiments both with and without dropout. But the real point here is that you can try to use this to predict, if I'm going to train a model of a certain size, how much data do I need to keep overfitting under control to some particular extent? So now I want to briefly move on and talk about how this generalizes to other data modalities. So there's some natural further questions. Were these results specific to language? Will they break down eventually at some point? A lot of people don't care about the test loss for a language model. What they care about is performance on some downstream task. And so it's a question of whether or not these results generalize in those cases. So this is sort of jumping to the answer in several respects. So first of all, these are compute scaling law curves, identical to the one that you saw for language, but generalizing to a bunch of different domains, including image models, math models, text models, which we'll talk about it again soon, multimodal models that predict images based on text or predict text based on images, and video modeling. So first of all, the claim is that if you train generative models in all of these domains with transformers, you see very, very similar scaling law type behavior. And I mean, you might be wondering, what is math? Math here is this mathematics data set created by some authors from DeepMind. They have sort of a bunch of code that procedurally generates a bunch of different kinds of math problems, calculus, algebra, sort of integer properties, measurement, all kinds of things like that. And you can train a model to predict the answer given a question on that data set. In some sense, that data set could be viewed as infinite because you can procedurally generate problems, and you even see similar scaling laws. The other point that is being made here, but is kind of implicit, is you can see in the title of the slide I wrote reducible loss. So what do I mean? Well, for many of these trends on data sets other than language, what you see is that there's some kind of irreducible loss, or you might call it irreducible noise in the data. In other words, if you actually make the scaling law plots like I was showing before, instead of seeing a power law, you see a power law plus a constant. And you get a very nice fit from a power law plus a constant. But you might not believe that power law plus constant is correct. You might think, oh, that's just some ansatz, but really it's some more complicated function. The functional form is different as the power law starts to level off. But what this is illustrating is at least for compute, and there are similar results for model size scaling as well. It actually seems like power law plus constant was the right ansatz. And if you subtract off the constant piece, you again get a very nice power law with log axes. So that's also what this is showing, which I think suggests that even if you see these scaling laws level off, like it's a power law plus a constant, at least for generative models, you are actually sort of continuing to learn more semantic information about the data set by going to more compute. And the other thing that you can do with the plots on the last slide is you can again ask, what is the optimal model size as a function of your compute budget? And in the case of language models, I told you it looks like that is itself a power law, and that there's some nice scaling where if you want to, as you increase your compute budget, you should increase model size by some amount. Now, I would have guessed that that scaling relation itself depends a lot on what kind of data you're studying, whether it's language or image data or multimodal, captioned images, whatever. I would have thought that maybe how you should scale up your model with your compute budget would depend a lot on what kind of data you were studying. And so I was at least somewhat surprised to see that if you put all of the data on one plot, which you can do, right? Because you're asking the question, what is the optimal model size for compute? That doesn't have anything to do with the value of the test loss. It seems like that is also quite universal, where for all of these different kinds of data sets, if you're modeling them all with just some autoregressive transformer, roughly speaking, you should scale up your model size with your compute budget in the same way. So this is sort of showing this now. I mean, that's not super precise. I mean, there might be a factor of 10 difference in what the optimal model size is, but I think the fact that the slopes of these are all very similar, I at least found kind of surprising. So at least that is quite universal.
So sorry, may I interrupt you in there?
Sure.
like you're talking a lot about the compute. I'm not sure if I understand correctly what you mean with the compute, because in my understanding, like your model size depends a lot on the quantity of data that you have. Also, if you have less data with the great model, with a big model, I mean, you will overfit very fast. So
Great. So this is all in the infinite data limit. This is all in a situation where the test loss and the training loss are identical and you're not overfitting at all. So this is in all cases, these are forms of data where we have a lot of them. And so we're not constrained by data set. If we were constrained by data set size, then it would be, then it would be very different.
All right, thanks for the clarification.
Great, yeah, thanks for asking.
So there are a couple questions from the chat about the couple slides. Just to quickly rattle them off. For the plots in the previous slides, are the curves, the fit consistent across? Oh, sorry. Are they consistent across varying the optimization algorithm?
I have not. So these are all with well-tuned Atom. I have not tried other optimization algorithms.
I see. For the video subplot, why is the trend less clear in the beginning?
Oh, great question. So yeah, that's a great question. So what's going on there is we really scanned model size over a large range. So the smallest video models here have only a few thousand parameters. And of course, I haven't told you all sorts of details. So these video models are using a VQ, like a VQ VAE kind of VQ encoding scheme. And so they are, I believe they're 16 by 16 by 16 videos. So the VQ code is 16 by 16, and then there are 16 frames. And that is a lot of tokens, like the size of the context is very big. So the two video models that are off trend at the beginning actually have a number of parameters which are of order their the total context size that the transformer is attending to. And this is sort of a conjecture. I don't know for sure, but my guess is that they're underperforming because I mean, the number of parameters in the transformer is so small that it's barely able to sort of distinguish all the different positions in the context. But that's actually, I mean, that's a speculation. I don't have sort of an empirical proof that that's why.
The video, you're keeping the VQ, the word bank size the same, like the what's a like when they
so the VQ codes, so I guess I'm abstracting out the VQ code. So I have a lot of images. I train some VQ encoder on a lot of images, and then I just fix that VQ encoder and I use it for all of these videos.
I see. Okay. Okay. Next question: are the dashed lines or the dashed lines correspond to the same power law exponent for all of these?
No. Yeah. So that's a great question. So I would have been. So I think that wouldn't. Yeah, that they're just not the same power law exponent. So the exponent is smallest for text. It's around 0.076 or so. For images and math and multimodal, the exponent is somewhere between sort of 0.1 and 0.25. It varies as a function of image resolution. So I haven't shown this, but I mean, you can study images of different resolutions and you get different exponents. So yeah, my apologies. I'm just, I'm not giving you a lot of those details, but yeah, the exponents are definitely different. The exponent definitely depends on the data set that you study.
By the way, these are all in the infinite data limit, right?
These are all in the infinite data limit, yeah.
Okay. Sounds good.
Great.
Sorry, quick question.
Sure.
Even if you assume infinite data limit, you implicitly perhaps making some assumptions about the distribution of data, where's the data coming from. So it still seems like the data might be coming from some sufficiently large and perhaps complex distribution, but this distribution perhaps doesn't cover all possible data distributions that you may encounter in future. So there is kind of nothing here that would prevent those models from breaking apart when presented with sufficiently orthogonal out of distribution data, right?
Absolutely, yeah. I mean, I'm not making any claim that out of distribution performance has some specific scaling here.
Although I understand that the notion of in and out of distribution gets very hazy, especially with infinite data set limit. But yeah, anyway, it's kind of orthogonal question. And here, as you said, you do assume that it's infinite data limit, therefore training and test, the boundary is again non-existent anymore. Okay.
Yeah, that is all correct. Yeah. I actually can make some comments about out of distribution generalization, but maybe you could ask again at the end.
Sure.
I think the simple one sentence is I think out of distribution performance basically just depends on in distribution performance if the out of distribution data is at least somewhat similar. So I think there do tend to be nice sort of scaling relations where sort of out of distribution you do worse, but I think you do worse in a relatively predictable way. Obviously, if you just make, I mean, if you're studying images and you replace all the images with like some random noise that you decided you liked, I mean, obviously that's I don't know what to say, but at least for sort of reasonably similar data sets, I think that's true.
Yeah.
And so, yeah, finally, I just wanted to say, you might ask, what about downstream performance? So you might not care about, say, image generative modeling. You care about, say, ImageNet classification. And so a thing that you can do is take your image generative model and you can fine tune it. You replace the embedding. You say mean pool over all of the outputs of the transformer, and then you can train a classification net on, say, 32 by 32 ImageNet, and you can study what the class. This is literally the classification error. You can also study the loss on ImageNet. It's very similar, but you might care most about, say, the classification error rate, 1 minus the accuracy, and that also seems like it scales very nicely with model size. And further, what you're seeing here is the orange points are just taking a randomly initialized transformer of that size and trying to train it on ImageNet classification. And the blue curve is what happens when you pre-train on this large generative modeling data set and task for all of these models. And then you fine tune just on ImageNet classification. And you see that larger models that are pre-trained are very, very consistently scaling and doing better at ImageNet classification after fine tuning. And furthermore, of course, the pre-training is helping them learn some sort of features that make them much better at ImageNet classification when they're bigger and help to avoid overfitting. So the claim here is just that scaling laws and the loss also translate to downstream tasks in a useful, interesting way. And finally, I just want to say sort of scaling laws are everywhere. For multimodal models, a cool thing that you can look at is what is the mutual information between, say, the image and the text in a multimodal model. Since you're modeling the probability distributions, this is really a thing that you can just compute. And so interestingly, the mutual information between, say, the image and text has some nice scaling law where once the model's big enough, it starts to improve, which means the model's really learning about, say, information in the text in order to know how to generate the image and vice versa. So I think scaling laws are really kind of all over the place.
All right, like what are you measuring there? Like mutual information of what?
Yeah, so this is the empirical mutual information. So I can take a, let's say I have text to image. So I have a model that first reads some text, like a caption, and then tries to actually make the image. So I can compute the loss on the image given the text, and then I can compute the loss on the image if I replace the text with something blank. Now, you might worry that this is out of distribution. So in order to avoid that issue, we retrained these models before making this plot on exactly the same data set, but sometimes with a caption and sometimes where the caption was just replaced by no text. And then we measured the difference in the loss on individual images when we have the caption and we don't, and we subtracted. And that gives you an estimate of the sort of empirical mutual information that the model is seeing between the text and the image.
Sounds good. Thanks.
Yeah, so now we can ask a question, which is sort of what happens if we just scale up language models. And my apology, I mean, I think we technically only have 5 minutes left, so I'll try to go through this quickly. So the GPT-3 model was motivated by, to some extent, asking this question. That was one of the motivations. And in our paper from January, we sort of stopped at order 1 petaflop days of compute, but GPT-3 goes all the way up to around 10 to the 3 petaflop days of compute. And you see that the sort of scaling law trends seem like they're, with compute, seem to be continuing. Maybe GPT-3 is a little bit off trend or above trend, but it's kind of hard to tell. And an interesting feature of GPT-3 is that it can do in-context learning. So the idea here is that, of course, there's learning via SGD, where we train the model. But you can also ask, if I show the model many examples of arithmetic or translation or anagrams, does it get better at performing at that task when it sees many examples in its context? Or when it sees, say, a natural language prompt that says, these are anagrams, please unscramble them and make a word. Those are the kinds of questions that you can ask. And so this is a plot of the performance of different language models of different size as a function of how many examples they saw in their context and whether their context included a natural language prompt. And this is literally for the anagram task you see in the middle above. And so there's some zero-shot performance. If you just show the model GAOT, does it say goat? And then there's one-shot and few-shot performance, where you increase the number of examples of the task that the model sees in context or show in a prompt. And you can see that accuracy is improving quite steadily, both with model size as we go from green to orange to blue, and also as we show the model more examples in its context windows. This is in-context learning. I mean, you might, roughly speaking, call this a kind of meta-learning. And it seems like the model is pretty good at it, and larger models are better at learning from examples. And so these are 4 different domains where we're studying performance versus model size, and for all but the top left, also performance versus how many examples the model gets to see in its context window. And so on the top right, we have SATs, like the SATs that American high school students take to get into college, and specifically analogies. Bottom right, we have Winogrand, which is a Winograd schema test. Winograd schemas are things like a tree fell on my roof, and so we got it fixed. Does it refer to the tree or my roof? And a human is supposed to know it's obviously my roof. So Winograd schemas test that kind of language understanding. Trivia is kind of self-explanatory. Arithmetic is self-explanatory. And so what we see is in different ways, larger models are performing better and better without fine-tuning on all of these tasks. So none of these models have been fine-tuned for that task at all. There is no fine-tuning. All this model has done is done autoregressive prediction of the next word. That's all it was ever trained on. It never was asked to do any of these kinds of problems or trained on them specifically or intentionally. And you can see that performance is improving with model size. I think maybe one of the most interesting things is that some of these improve very, very smoothly, like trivia. And others, like arithmetic, there's some sudden change where suddenly between, say, 6 billion parameters and 12 and 175 billion parameters, the model kind of learns to do arithmetic. I mean, I think that's very interesting, that some kinds of skills can just kind of suddenly emerge. These models have been trained on exactly the same data, but larger models are sort of suddenly learning this thing that we think of as some kind of crystallized idea, like you understand arithmetic or you don't. So I think that's striking. And in many other cases, there's some smooth improvement. And these models are doing very, very well. On SATs, the average college-bound senior for this SAT test got 58% of them right. So the largest model here is doing better than the average American senior high school student who's planning to go to college. Another example of that is whether or not you can tell samples are made by GPT-3. So we studied randomly generated news articles that were sort of a few paragraphs length and asked real people which one was written by an AI and which one wasn't. And you can see that as you make the model bigger, it's getting harder and harder to tell whether the text was written by an AI or not. And by sort of the GPT-3 model scale, it's almost at chance level. And I mean, I think these kinds of capabilities are extremely interesting and also extremely scary. And we sort of need to do a lot of work to be able to make these models safe. And at least for me, that's actually a significant part of the motivation for thinking about these questions. So some implications. I think these results suggest that there aren't conceptual barriers preventing us from training more powerful models. I think that these scaling laws are surprisingly precise. And at least for me as a physicist, whenever I see something that's very, very precise, it really makes me want to ask, why is this happening? And what does it tell me about how these systems work? I think it also then suggests some abstractions that are useful for thinking about progress and research, which is that you want models and techniques that sort of scale well and achieve some nice scaling law, and you want to conversely avoid bottlenecks that prevent further improvements in performance. And I think if you sort of just make plots, you can find that there are a lot of scaling laws everywhere in machine learning research. And at least for me, they kind of like help organize my work and my thinking. So, I mean, this is kind of a caricature. The bottom left is supposed to be a joke. So I think if you've read the machine learning literature, you'll have seen a lot of tables that look kind of like this. There's some benchmark and there's various different models, and you say, look, my model won, and so what I did worked. And I think for me at least, I think of success more in terms of a line rather than a point. I mean, you know that transformers are greatly improving on LSTMs because as you scale them up, they just consistently do better. And I think this is sort of a useful way of thinking about, at least for me, what techniques really work and what might not work. So that's the end of the talk. So I'll just conclude. Model size, dataset size, and compute are, I think, in many ways kind of like macroscopic thermodynamic variables governing machine learning performance. And optimal loss seems like it obeys very predictive scaling laws. And it seems like performance really meaningfully keeps improving, both on the test loss itself that we're optimizing and on downstream tasks, if you aren't running into some form of bottleneck. And I think we're really just beginning to understand how and why these systems work. And I think there's a huge amount more to do. And I think the way that physicists tend to approach these kinds of questions can be extremely productive and informative. And so I encourage everyone to think about these questions. So that's it. Maybe I should take some questions.
Thanks, Jared. So let's go to the questions. Okay. So from Natarshan, has there been any follow-up work at OpenAI exploring the region beyond 10 to the 4 petaflop days?
I don't know. I think that's the kind of question I can't answer.
Yeah, sounds good. Do you anticipate data becoming the biggest bottleneck in the near future in terms of scaling?
I think the answer is no. So I mean, in the GPT-3 paper, there was a data set that was, I think it was about 300 billion tokens. I think the internet has a lot more data than that. And I think that was sort of basically avoiding overfitting for the biggest model we trained. So I don't think in the near future. I can imagine if you really wanted to continue this kind of program, it eventually could be a problem, but I think it's still a ways away.
From Frida Ron, what are the details for the multimodal results? Does multimodality help for the individual modality? Is it more data efficient?
Yeah, so here's a great situation where I think that architecture matters and really doing something sensible matters. So I'm a physicist, so I'm very happy to sort of do a very simple thing and just sort of see how it behaves and how it scales. I don't think that the multimodal models that we trained are the best architecture to use to study multimodal data. I don't know that they're super different from the best architecture, but we literally just use a decoder-only transformer where so there's this embedding space. So the embedding space is literally the concatenation of the language embedding space and then the pixel embedding space, which is just 256 colors per pixel. So it's really just a decoder-only transformer that looks at either the text and then the image or the image and then the text and tries to autoregressively model either every language token when it's studying language or every pixel of the image. So I don't think that this is the best way to do that task. If your goal is to, say, generatively model images based on text or vice versa, I don't think that this simplest possible thing is the best way to do it. So in that sense, like, I'm not advocating that anyone do that, or that I think you can probably improve the overall factor of performance in terms of downstream tasks, just in terms of the modeling task by some factor that's probably significant, like a factor of 3 or 4, by doing something smarter there. I mean, in the paper that should be coming out soon, we definitely give more information about many of these scaling laws and the multimodal model, but I don't think the performance of these models is impressive. But what was interesting to me is that on this very different kind of data, they exhibit these scaling laws.
From Charles Foster, can you talk about why large models are more sample efficient? This is a surprising finding.
Great. So, I mean, I think I don't know any explanation theoretically for this that is satisfying. So larger models with the same amount of data or the same number of steps achieve a lower loss. Eventually, if you fix the total amount of data, then this stops. So if you're bottlenecked by data and you just keep increasing your model size, then you really end up being data limited. You end up in this regime that I showed in kind of the very first set of plots, where data set size is governing performance. But it is definitely the case that the learning curves for larger models lie below the learning curves for smaller models, and I don't have a theoretical explanation for that. That isn't just sort of hand-waving speculation.
From Guillermo, any new ideas on the contradiction on section 6.3, figure 15? So Guillermo, do you want to talk about what you exactly mean?
Well, I mean, like the contradiction is explained on the paper, right? It's like the fact that when you trained in I think it was the optimal way with a certain compute budget, which you did without basically with one epoch, right? Without repeating on any data sample, versus the learning curve that you obtained by assuming you all of the data samples you observed. Instead, you trained to convergence, which I think is the one that has a shallower curve, right?
Yeah.
And then you of course find this surprising. So I was curious if there was any updates there.
Yeah, so there are kind of. So I think the update that I would give. I mean, I wish I had the plot to show you. I don't have it in these slides. But I mean, it's in this paper that should be out soon. So I think actually maybe the best way to look at this is a little bit simpler. So it's possible to draw all of the learning curves for a model on the same plot as this data set size scaling relation that you see in the center here. So how would you do that? Well, you could say for the learning curve, I can just ask how much data has the model seen already during training. And if it has plenty of data, then that's just going to sort of keep increasing during training. I can ask basically how many tokens have been processed by the model during training. And I can put all of those learning curves on the same plot as the dataset size learning curve. Now, since the dataset size learning curve is obtained by taking a very large model and training to sort of convergence in terms of early stopping, getting the best possible performance, which means training for many epochs typically. The dataset size curve, this line that you see in the center, is always going to lie below, by definition, all of the learning curves that you put on the same plot. Because if they were to coincide, that would mean that by training for only a single epoch, a particular model was able to achieve the best possible loss it could achieve by training for more epochs and early stopping. So okay, so you can make a plot. You can imagine this, at least if you're fairly familiar with these kinds of plots. You can imagine all of the learning curves for different model sizes on the same plot as this data set size plot, bounded by the data set size plot. And what really is happening, I think, is that as you train larger models for longer, the learning curves are starting to approach the data set size curve. So what's happening is as you train big models for a long time on a lot of data, basically SGD is getting you in one epoch very, very close to the performance that you could get training maybe for multiple epochs and early stopping. So I think that's kind of what's happening.
I mean, that's the intersection point you found.
Yeah. So that would be the intersection point. And so what I think this means is, I don't know for sure, this is then speculation, is that if you continue the compute plot beyond the intersection point, you'll be training for only one epoch and you'll be hitting the data set size plot. And so I think that the data set size scaling will be the thing that takes over and determines subsequent performance asymptotically. I don't have a proof of this. This is sort of speculation. I do not have an example where you can see beyond this intersect, where you say have nice scaling with compute and data set size, and then you can look beyond the intersection point and just see what's happening. But my guess or conjecture would be that data set size scaling is then what controls performance.
Yeah. Okay, that's quite interesting. Yeah, I mean, I will be curious to see, because you have shown, for instance, the math data set has a steeper slope versus optimal compute or whatever. So perhaps there's some example where we could see the intersection point happening earlier, and therefore we could.
Yeah, that's a great question. I mean, we've observed this phenomenon also for images. That's one example where we checked, and there the intersection point was not soon enough that we could study it. The intersection point also is extremely sensitive to these exponents because you're sort of asking when two fairly shallow lines intersect each other. And so if you get the exponent wrong by like a few, I don't know, 5 or 10%, the intersection point might move out to like 10 or 100 times more data or compute. And anyway, so yeah, we have not gotten there yet, at least in any experiments I'm aware of.
Thanks.
Okay, from AK Roy, how can we make the test loss versus compute log plot sublinear?
Sublinear. You mean how can you make it? How can you do better than like get something better than the scaling law?
I'm not sure. AK Roy, are you here? Okay, I don't know what is meant here, so maybe let's move on. Okay. Ethan Cavallari, I think the question you're asking here is the same as Guillermo's question. So can we move on? I take that as yes.
Yeah.
Aaron asks, have you tried something like mixture experts from Shazir et al.'s paper to increase parameter count without increasing compute?
That's a great question. I haven't tried it. I think it's an interesting avenue for research.
From Abinov, for language models, do you have any insight into data quality? The T5 paper seemed to suggest training on Wikipedia plus books versus filtered common crawl didn't make a big difference.
I'm not an expert on this. My impression is that data quality does matter, but I mean, I think like I think the difference between, say, like the web text data set that's been used in some of these papers and just common crawl is meaningful. But it's not something I've personally studied.
From Sheer, I saw a section about why scaling laws. Would be interesting to hear more about that and also ask the following. In physics, scaling laws are often related to universality classes. Is there any sense of something like that here?
Yeah, so that's a great question. So, I mean, I can just show you this slide. This is sort of a very general speculative kind of theory for why these scaling laws might occur. And with my student Yudkar Sharma, we did some experiments that seemed to support this theory, but I wouldn't be sure it's correct. So the idea is very, very, very simple. I mean, it's like a physicist's toy model. So you can imagine that all a model might be doing is mapping the data to some manifold, which has an intrinsic dimension d. I mean, this isn't a linear manifold, this is a manifold. And then all it's doing, say we take the simple case where you're just, say, doing regression, you're just trying to model a function on the data. Then it's basically, you could imagine that you just map the data to this manifold, then you chop the manifold up into some number of pieces. You approximate the function as sort of piecewise constant or piecewise linear inside each of these pieces. And that's all you do. So this is like a toy model for what machine learning models might actually be learning to do. So if you were to do this, then if you have some continuous function on the data manifold that you're trying to imitate, you're trying to regress to, then the error, the loss, is going to be proportional to the size of the regions in which you've chopped up the data manifold. For the simple reason, I mean, the error you get from approximating as a constant or piecewise constant scales as sort of the size of these regions. However, if the manifold has d dimensions, then if you increase your parameter count by some factor, then you actually can only zoom in and make these regions smaller by an exponent that's of order 1 over d. Or maybe to say it more simply, if you decrease the size of each of these pieces by a factor of 2, then you need 2 to the d more parameters to model piecewise constant functions in each of these 2 to the d times more regions. And so what this suggests is that you would get a scaling law with model size that goes like 1 over the model size to some exponent which is of order 1 over d. And there's a 4 on this slide because if you use piecewise linear approximations and the loss is MSE, then sort of that's what you get from a very naive analysis. And so this suggests there's some relationship between the dimension of the data manifold that the model maps its data to and the scaling exponent you find, and that this somehow explains the scaling laws. So we did some experiments on very simple data sets, a lot of them teacher-student type experiments where we had explicit control over the dimension. We did some other experiments where we tried to measure the dimension of the data manifold in some way. And we seem to find that this sort of worked, at least for these simple data sets and simple experiments. So that is a theory. I mean, I think there's a lot more to do and to explore to try to validate and understand this theory, but that is a theory for why you would get scaling laws with model size. You can also, you can also extend this to a data set size scaling by saying that you could imagine that you have points on the data manifold and your model is basically just interpolating between those points. I mean, this is something that was emphasized to me by Yaseman Bari. I mean, I think other people have thought about this as well. And so this might explain both something like model size scaling and data set size scaling. I think it doesn't explain compute scaling, but that's the idea.
But it doesn't give any hint as to universality, I guess, or doesn't even suggest any universality.
Yeah, I don't think that these are critical exponents. I mean, it's a kind of universality. It suggests that all of these different data sets just get mapped to different data manifolds, and the exponents that we see, which are different for different data sets, are just measuring that dimension. Sure. So that's, I mean, but it's not the kind of universality that you talk about in critical phenomena or anything like that.
Right. Yeah.
Jamie Simon asked something similar. I think the one thing that's notable in the question is whether there's an applicable renormalization argument that could explain it.
I mean, I guess this picture is a little bit like renormalization in the sort of simplest sense that like you're chopping things up into smaller or bigger pieces. So, I mean, maybe there's some, I mean, like maybe the data manifold isn't exactly a manifold. Maybe it has some fractal structure or something, and there's some kind of renormalization idea there. But I think there's a lot of work to do to sort of make that precise.
Box asks, are there improvements to data quality itself which could improve training time or accuracy for larger models?
I mean, I wouldn't be surprised if there are, but I don't know much about that.
Yeah. Max asks, how do you reconcile that other papers have found similarly universal scaling laws, but end up having different exponents in the power law for the same task?
That's a great question. I mean, I think so. I mean, I think I think this is a very interesting thing to explore. I mean, like in this case, like with LSTMs and transformers, we saw a quite similar exponent. I think it depends probably a lot on what you're maybe what you're limited by. I think when you have a lot of data and you can scan over a large range, I would guess that you get fairly universal answers. But I think if you are kind of questionably bottlenecked on data, et cetera, then I think it's a little bit more subtle. So I don't know. I think I mean, I definitely think it's an open question whether the exponents are different for different architectures on the same task. I guess I would be surprised if they can be very, very different over a large range where there's like a nice scaling law, but I mean, that's just my opinion, man. So yeah, I think it's just worth exploring in more examples.
From Sylvester, why do we see monotonically decreasing test loss, whereas a double descent effect predicts a local maximum at a certain model size?
Yeah, so I think, okay, so I mean, I don't know for sure. My impression is that double descent almost never happens if you early stop. So if you measure your test loss or your validation loss, and then you just stop at the point where that's lowest, I think that it's at least much rarer that you would encounter a double descent phenomenon. The other point here is that most of these scaling laws are, as I said, only being limited by one thing. So you have infinite data and you change model size, or you have a really, really powerful big model and you change the data set size. You're not you're not kind of changing, you're not limited by a combination of both. I mean, there are some scaling laws like these where you change both the data set size and model size. I mean, I wouldn't take this particular ansatz that's written on this slide, this equation, to the bank. But I mean, I think that there are some nice scaling behaviors there. But again, then we're using early stopping, and I think double descent almost never happens with early stopping.
From Alex Fields, how do you think about the societal implications of increasingly powerful models following these scaling laws?
I think it's absolutely huge. So I mean, honestly, I mean, the reason why I'm working in this field, I think at all is, I mean, probably at least 50% because I'm very concerned about these kinds of implications. I think that, I mean, there's a lot of hype around machine learning. There are people who think that machine learning is just sort of like overhyped. I'm not one of these people. I think it's going to have huge implications for society. I think that's going to happen really fast over the next 5 to 10 years. And I mean, one of the motivations you could ask, well, why am I working on these things? So I think there are several. One is I think better understanding why these models work in general, and then why they're improving, helps us to sort of figure out what capabilities are going to arrive and when, and that sort of thing. I think just more fundamentally, understanding a scientific field better helps you sort of to make it safer. I mean, I think it's always safer when you understand what you're doing rather than if you don't understand what you're doing. So that's one thing. I think also a lot of questions revolve around sort of scaling for sort of being able to make these models more robust, being able to make them more aligned with our interests. So I think the kind of thing that one of the things that I'm working on now is trying to understand things like, are various techniques going to, like, as models become more powerful, you might, on the one hand, think that they become more dangerous. I think that's a significant worry, but also if they sort of understand the world better, it might also be easier to teach them more cheaply and effectively to sort of be aligned with what we really want. And so I think I'm very interested in questions like, are safety techniques, like say using human feedback, going to improve faster than, in some sense, model capabilities? And sort of what does that imply for society? So I mean, I'm very, very motivated by this. A lot of my involvement in this field came from talking to a lot of friends who are very concerned about this. So I think it's really a big question. I think we're going to confront it sooner than many people think.
From E.K. Roy, any insight on how to make the compute more efficient? Currently, test loss versus compute seems to say that we need 10 times the compute to get a 10% improvement in test loss.
I mean, that's a great question. I think that's what, in a sense, like the whole field is working on. So I mean, mixture of experts was mentioned by someone else, which might make you more compute efficient. I think that's interesting. I think there are a lot of ideas like that. I mean, I would be very impressed if we can change the exponent in the scaling law. Maybe that's possible. I think that's probably really hard, but I'm sure we can change the prefactor. I'm sure we can make efficiency improvements just in terms of very pure engineering, as well as maybe architecture improvements, training on higher quality data. I'm sure there are a lot of ideas out there. That's what I think a lot of the field is working on for making these algorithms more efficient. But yeah, my conjecture is that we would change the prefactor rather than the scaling exponent, but I'd be very excited to be wrong about that.
From Ethan, wouldn't video have more entropy that needs to be modeled and hence bigger model than language? Why was the optimal model size for video the same as the optimal model size for language?
Oh, great question. So that's the optimal model size as a function of your total compute budget. So the claim isn't that so I mean, this optimal model size is a line which depends on compute rather than a point. So if you have if your compute budget is say 1 billion times bigger than any value on this plot, then you would want to train a much bigger model. But the question is just if you're trying to get the best model for your compute budget, what should you do? And so the claim here is that roughly speaking, it seems like all of these different data sets exhibit the same kind of scaling law for that. I should also say that these models are really dumb. I mean, I think I said that about the multimodal model. I mean, I think the language model is not that dumb. It's a pretty reasonable way of modeling language. But I mean, the video model and the multimodal model are very, very naive. I definitely am not claiming this is the best way to model video or multimodal data. So maybe this changes if you use a different encoding for your data or a better model architecture. I don't know, but at least if you just use an autoregressive transformer on pixels or VQ code pixels, then this is what we see.
Does that mean it probably doesn't have to do with entropy then? Because like even for a fixed compute size, I feel like you'd expect the amount of parameters for video to be like way bigger than the amount of parameters like for the optimal model size for language.
Yeah, so I mean, I'm not sure exactly what you mean by entropy. If you mean something like
video has way more entropy, like just more bits that you need to like get into the parameters.
Yeah. So I guess the test loss that I'm showing you, I mean, I think it's just an overall factor, but the test loss I'm showing you is averaged over tokens. So it's like test loss per token. Of course, I don't even have a scale on these y-axes, but yeah, that would on this log plot just sort of shift the curve up or down, but it wouldn't really change its shape.
Okay, so from Box, what are some challenges you expect to get to the trillion parameter size models? Is it just about money?
Yeah, I mean, that's either a question I can't answer or the answer is yes. I don't know. I mean, given that this is deep into the question section, I mean, I come from particle physics. I think like for me, the field, well, I mean, maybe everything that I've said in this talk is wrong, but say you believed or gave a fair amount of credence to the kinds of things that I'm saying in this talk, you might like imagine that like the ML field organization is a little bit weird. So I mean, in physics, we have experiments that people do in the basement of the physics building, and there are a lot of interesting such experiments. But we also have experiments that cost $10 million, $100 million, $1 billion, and I think even like $10 billion. Like the Large Hadron Collider, I mean, costs a lot of money. I mean, I think it costs something like order 1,000 times more than GPT-3. So I mean, it seems like the ML field is very organized around like everyone doing their own experiments in their basement. There aren't large collaborations of ML researchers who band together and train really big models and then get all of the payout from them. I mean, I think from these models, there's a lot of experiments you can do. I mean, with something like GPT-3, there are a lot of interesting linguistics and cognitive science experiments. There are interesting ML experiments. There's all kinds of stuff to do. So yeah, I don't know. I mean, to me as a physicist, it's really weird that that there aren't any large collaborations doing this in ML. And the only way you can try to be in some such collaboration is to work with a few big labs. Yeah, so I don't know. I mean, if I was a famous ML researcher, then maybe I would try to do such experiments in an academic setting, especially if as an academic I thought that that it was important for me to sort of have access or control to these big systems. But so far that hasn't occurred. So I find it somewhat mysterious that it hasn't occurred, but maybe it just takes a long time.
You should go ask Jim for money. He's got rich lately from the grant.
Okay.
Okay, so Juan asks, Tishby came up with the theory for scaling laws for simple models in the 90s. Perhaps these ideas are relevant here. I don't know if you know about these ideas.
I think I've seen this. I think I've seen a paper by Tishby from the 90s. I wasn't really sure. I don't remember exactly what was said. I mean, I think. Yeah. So, I mean, I think if you have a very specific theory in mind, I'd love to hear it.
Yeah. So maybe like take this offline or something.
Yeah.
Yeah, and I think that's all the questions. But I do wonder, do you have other slides explaining kind of the theory, coming up with a theory behind it, other than the simple model you had?
No, I mean, I only have these 2 slides. There's a sort of like half page of math you can do to compute this for, but that's all I have in terms of things that are complete. I mean, I've been doing some work with, I mean, maybe some of these people are here, like Jae-Hoon Lee and Ethan Dyer, Yaseman Bari, and Yud Karsh, that explores this further. I think that there's a very nice link between this theory, which is very vague, but as a physicist, I'm sort of happy with vague theories. I mean, I'm like I'm not like interested in theorems necessarily. So I think there's a nice connection between this and linear. So there's the linearized limit, which is sort of the NTK limit of networks, where you basically just get a linear model. And then in the case of linear models, I think there's a nice connection between this kind of dimension of the data manifold idea and the spectrum of the kernel that you identify in this way. Basically, if the kernel has a spectrum of eigenvalues with a particular power law spectrum, then that implies that you'll get a certain scaling law for a linear or linearized model, and that has some connection to this data manifold idea. So that's a little bit more rigorous, but maybe a less restricted, more restricted domain. So we're trying to work on that. There are also some other scaling laws that I think are easier to derive, but that maybe are less important, or I don't know. It depends. Everyone's notion of important is different. So you can imagine that you have a model with, say you have a very big model, but you're limited by data. You can ask, what is the approach? So this is actually related to a plot. So maybe I'll show that plot. You can ask, what is the approach to the limit where you're only where you're limited by, I guess, your model size. So you can expand in like 1/d, and it turns out that there are reasons why you should expect a sort of 1/d expansion, which is analytic, like it's in powers of 1/d with integer powers. There's a kind of dual statement about model size, and so that's another kind of scaling that I think one can sort of show pretty reasonably rigorously, and I think is also experimentally true. So that's a case where the scaling exponent is sort of always 1. So those are some theoretical things I'm aware of. I mean, maybe there are many other things that other people know about.
I see. Okay, one last question from CRG. Do you expect the last bits of loss to reflect the missing common sense and such? Would small loss differences at the end continue to lead to big perceptual effects?
Yeah, so I think this plot is evidence that that sort of getting more bits of the loss matters, in the sense that I mean, if you look at the 32 by 32 image scaling law for just the loss, it looks like a power law plus a constant. And by the time you're at a 10 million parameter model for 32 by 32 images, you're starting to sort of approach this asymptote where the power law looks like it's leveling off into the region where it's like kind of close to the constant floor. But you can keep training bigger models and you get closer and closer to that seemingly constant floor. And that means that you're kind of scraping up the last few bits informally of information. And you see that, I mean, I said that around 10 to the 7 parameters, you're starting to get close to this floor. But if you keep training bigger and bigger models, they're learning features that are semantically useful, it seems, to do better on this downstream classification task. So I think that like these last few bits do contain semantic information. So that's in the image case. I mean, I would expect that that's probably also the case for language models. Of course, I don't know what you learn when, but I do think if you truly had literally infinite data and an infinitely big model and you could train it for as long as you wanted, I mean, I do think the model would learn everything about the data distribution. And in that sense, you'd get the common sense reasoning eventually. But I can't promise you when you'll get the common sense reasoning and whether or not it's sort of within reach. And I guess the only way to understand that is to look at these plots of like GPT-3 performance and ask sort of how big of a model would you need to get to sort of human level. And I think for different tasks it's different, but it's not infinitely far away.
Great, thanks a lot, Jared. That was a good talk, great talk, and also a long QA session. Right. So thanks for staying.
Yeah, thanks.
Yep, thanks for your interest. Yeah, and hopefully I'll talk to you all later. Bye-bye.
Yeah, thanks everyone. See you later.